Hi class, welcome to Online EdVantage. I'm Dr. Scott Adamson, and if you would, please subscribe to our channel. Now for this video, we're going to continue thinking about line integrals and the different strategies we can apply to compute line integrals. And in this case, I've set us up to learn a new strategy. In the previous video, we looked at traveling, metaphorically, through this vector field along the quarter circle counterclockwise from 1, 0 to 0, 1. And we kind of convinced ourselves that that line integral should have a negative value, and indeed it did. We worked through it and we got a value of -2. Now, to help set the stage for this new strategy for computing line integrals, I want to ask you a what-if question. What if this vector field right here was actually a gradient vector field? What if f was the gradient, capital F vector field, was the gradient of some function f? Well, let me remind you what a gradient vector is. A gradient vector is, given some multivariable, in this case two-variable function of x and y, a gradient vector would be the vector consisting of the partial derivative with respect to x, I, plus the partial derivative of f with respect to y, j. So, what if 2x plus 3y was actually a df dx, a partial derivative with respect to x? And what if 3x minus 2y was a df dy? What if this was a gradient vector field? So let me just record what I just said. What if df dx was 2x plus 3y? And what if df dy was 3x minus 2y? Now, we're going to explore this and see if this is the case. If there is a function f such that its partial derivatives are as we've recorded here, what might that mean in terms of computing the line integral? So let's think about this. What if this was df dx? Could we work our way back and figure out the function f such that df dx was 2x plus 3y? Now remember, this is the partial derivative with respect to x. If the derivative with respect to x turned out to be 2x, then the function must have been x squared. Notice I'm just taking the antiderivative. The derivative of x squared is 2x with respect to x. Now, if we took the derivative with respect to x and got 3y, now, when you take the derivative with respect to x, 3y would have been a constant, and so the function would have been 3y times x. The derivative of 3y times x with respect to x is just 3y. But now, do you remember with antiderivatives back in Calc 2, we have this plus c, this constant, because the derivative of a constant was 0. Well, in this context, the derivative of a constant is 0, but in the context of a partial derivative, that constant could be any function of y. So I could have had x squared plus 3yx, the derivative is 2x, the derivative is 3y, plus any function of y alone, and the derivative with respect to x would have been 0. Now, likewise over here, df dy, if this was a gradient vector field, then df dy would be 3x minus 2y, then f would equal, now, what did we take the derivative of with respect to y and get 3x? Well, 3xy. Look familiar? Notice our function f has a overlap here of 3xy. The function is going to involve 3xy. Therefore, the derivative with respect to x is 3y, the derivative with respect to y is 3x. So far, so good. Now, if df dy was -2y, then f must have had a -y squared, because the derivative of -y squared is -2y. Now again, we have this constant issue. If we're taking the derivative with respect to y, then this function could have had a constant function in terms of x alone. The derivative of any function involving x alone The derivative with respect to y would be 0. So now, kind of put these two pieces together. If this was indeed a gradient vector field, then there would be a function f such that df dx is 2x plus 3y, df dy is 3x minus 2y. So far, here's what we've got. That function f has to include x squared, because the derivative with respect to x, 2x. The derivative with respect to y would have been 0. We've previously seen that they both have a 3xy term. The derivative with respect to x, 3y. The derivative with respect to y, 3x. And this function would have to have a negative y squared term. The derivative with respect to y, negative 2y. The derivative with respect to x, 0. So notice this c of y, there it is. Notice this c of x, there it is. So we kind of piece it all together, and yes, there is a function f such that df dx would be 2x plus 3y. There is a function f such that df dy would be 3x minus 2y. So there is a function f, so that our vector field that we started with was a gradient vector field. Now, you might be asking yourself, so what? Check this out. Take this function f of xy, which is x squared plus 3xy minus y squared. Now remember, this whole situation was we were on a parameterized curve, a quarter circle from 1, 0 to 0, 1. Let's evaluate this function at 0, 1, the ending point of our path in that vector field. Evaluate this function at 0, 1. If x is 0, and y is 1. If x is 0, that's 0. If x is 0, that's 0. If y is 1, we're going to get negative 1 squared, or just minus 1 squared, or just minus 1. Evaluate this function at 1, 0. Remember, we were starting at 1, 0 and moving to 0, 1. So evaluate the function at the beginning point. If x is 1 and y is 0, so if y is 0, these two terms go away, but if x is 1, 1 squared is 1. Now, take f at 0, 1, subtract f at 1, 0. That is, take negative 1 and subtract 1, and you get negative 2. The same result we got previously. What I'm demonstrating here is what we call the fundamental theorem of line integrals. Notice the line integral turned out to be the function f, which came from antiderivatives of df dx and df dy to generate a function f. We evaluated the function at the end point, got negative 1. We evaluated the function at the beginning point, got 1. Subtracted them, got negative 2. The fundamental theorem of line integrals. Now, this strategy only applies in the case of a vector field that happens to be a gradient vector field. Not every vector field is a gradient vector field. In fact, these vector fields have a special name. A gradient vector field is fine, but we call such vector fields conservative. If you have a conservative vector field, then you can apply the fundamental theorem of line integrals. Find the function f such that df dx is the I component of your vector field. df dy is the j component of your vector field. Evaluate that function f at the ending point and the beginning point. Subtract, just like the fundamental theorem of calculus from Calc 2, and boom, you've got your line integral. Now, we're going to continue this thought because there's some other issues here with conservative vector fields, so please continue to the next video to learn even more about line integrals in the context of a conservative vector field.